Welcome to WaveMotion. We're into our synoptic scale features, and we covered fronts, vertical cross sections, jets, types of atmospheres, and now it's on to how waves in the atmosphere move. So we're going to start out describing waves, and then we're going to talk about two different types of waves in the atmosphere. We're going to look at long waves and short waves. Long waves move by barotropic instability, and short waves by baroclinic instability. So first, waves. If you look at any weather chart, you'll see a wavy pattern. In this picture, you're looking down on a hemispheric map, looking straight down on the North Pole, and you can see areas, well, you can see waves. You can see troughs and ridges. And weather patterns can be described as waves. As you know, a wave is a repeating pattern with some periodicity in time or space. So we look at our upper level patterns as series of waves. And as you know, the wave has characteristics of amplitude, wavelength, period, wave number. Wavelength is simply the distance that the wave repeats itself from crest to crest or trough to trough, typically measured in kilometers. Amplitude of the wave is its maximum value, or the height of the wave, also typically measured in kilometers. And then the wave number is the number of times that a wave repeats itself in some given distance. So you define the distance and then you count the number of waves. And finally, the phase speed is how fast the wave is moving, or the wave is propagating. In meteorology, we usually describe that in terms of knots for large-scale waves. So in the atmosphere, you've got long waves and you got short waves, and we kind of talked about these already. A long wave, my gosh, there's the definition of long wave from the glossary of meteorology. But you know, it's a wave, a major wave that is in the planetary in the westerlies, basically. It's a big wave. It has a very big amplitude and also a very large wavelength. And you know, the wavelength is really big. It's bigger than, you know, cyclonic and anticyclonic systems. We call these planetary waves. And here's some pictures, or actually a picture of the hemispheric pattern. And you can see on this particular one, I identified troughs. And the major troughs, the really major troughs, you can count them around the planet. You've got, around the hemisphere, you've got, it looks like five major troughs. So those are your longer planetary waves, and you can say that the wave number across the hemisphere is 5. We've got five waves. Short waves are a little bit different. These actually move through the planetary waves and move in the same direction as the basic current, and their wavelength is relatively short. And a lot of times you'll see these short waves superimposed upon the longer waves. So here's a weather map showing you trying to pick out all the little short waves, all the little dips in the atmosphere. This is looking at 500 millibars, and typically we look at 500 millibars for whenever we pick out short waves. Actually, the better chart for picking out short waves is 700 millibars, because your contour interval at lower altitudes is only 30 meters, whereas at higher altitudes it's 60 meters. And if you go all the way up to the jet levels, at 300 millibars it's 120. So you get a little bit better resolution lower in the atmosphere. And 700 millibars is a really good place to pick out short waves. So the way that these waves move, short waves and long waves, are different. Long waves typically move as a result of vorticity. We call that barotropic instability, whereas short waves are more a result of temperature advection. And you remember when we were talking about temperature advection, we said that that was a purely baroclinic atmosphere. So short waves move by baroclinic instability. In our next PowerPoint, we're going to talk about barotropic instability and what that means and how long waves move.